In Chapter 5, we learned about the binomial distribution. It's a discrete probability distribution that satisfies 4 requirements. If n is large, n being the total number of trials in the experiment, the formula for the binomial theorem can be very difficult, if not impossible, to calculate by hand or using a simple calculator. And sure, technology is amazing nowadays, and we can likely calculate that binomial experiment very quickly using something like Google or Excel. What we're going to talk about in this section, though, actually is a connection between the binomial distribution and the normal distribution. The normal distribution, if you recall, is a continuous probability distribution. We have a reminder from section 5.3 about this binomial experiment and the 4 requirements. Also, recall that a binomial distribution is ultimately determined by 2 values. The first value, n, is the total number of trials, and p is our probability of success. In this section, we're going to look at how to use a normal distribution to approximate a binomial probability distribution. For our binomial distribution, if we know p and n, we also pick up q, which is 1 minus p. If 2 conditions are satisfied, n times p is greater than or equal to 5, and n times q is greater than or equal to 5, then we can approximate probabilities from a binomial probability distribution reasonably well by using a normal distribution. And the normal distribution will have the parameters of a mean, m times p, and a standard deviation, the square root of n times p times q. Notice that these are exactly the same as our binomial distribution. So n times p greater than or equal to 5 and n times q greater than or equal to 5. Here we have a graph where the probability is 0.5 and n is 10. So we can see that n times p, 0.5 times 10 will give me 5, which is greater than or equal to 5. And n times q is also 5. So I'm satisfying those conditions. The blue bars represent the binomial distribution. And remember that that's a discrete probability distribution. PDF is short for probability distribution function. And the normal distribution is the red curve, and that's a continuous probability distribution function. And we can see that the curve follows those bars reasonably well. The other thing that I want to point out is exactly where these bars happen. If I trace the bars, I want you to notice where the edges of the bars are falling in relationship to the whole numbers on the x-axis. So here, for example, that value is not 0 and it's not 1, it's 0.5. And the second value, 1.5. So the probability in a binomial distribution of exactly 1 in this graph is given by the area of this bar, which spans from 0.5 to 1.5. And we can keep going with it, 2.5, 3.5, 4.5, etc. This will become important to us in the approximation, using the normal to approximate the binomial. The other reason that we study this is because when we move into inferential statistics on proportions, proportions can be thought of as a binomial distribution. Either you have the attribute that we're looking for or you don't. So there's a probability associated with that success. When we are looking at inferential statistics, we use the normal distribution approximation. So we are going to use what we learn in this section, the fact that the normal can be used to approximate binomial distributions, when we move into inferential statistics. When we use the normal distribution to approximate the binomial distribution, we cannot just do a simple one-to-one shift. I cannot replace the word binomial with normal. It will not give me close enough values. Remember that normal is continuous, so all of the numbers between 0 and 1 have a probability in the normal distribution. We have to use something called a continuity correction. A continuity correction is used when a continuous distribution is used to approximate a discrete distribution. This means that instead of using a single value, like x equals 4, in the normal distribution, we use the boundary values of 4, 3.5, and 4.5, just like in our last graph where the bars were falling on the boundaries of our numbers. We need that information. In the table, as a summary, I have the different kinds of probabilities that we'll be looking for and how we would use the normal distribution to approximate it, what the continuity correction should be. I encourage you to draw the pictures. It will help in visualizing and understanding what it is you need to find the probabilities of. Remember, we're always looking for probabilities which are equivalent to areas under the curve of these graphs. And I have a visual here drawn as well to help in the comparison between the two. So the first column is the binomial probabilities. This second column is how we change the values to use the normal distribution. And then the third column is our visual associated with it. For the normal distribution in the middle, we're going to use the same procedures that we did in 6.1 and 6.2 to find probabilities. So if we're finding probabilities between numbers, we need to subtract 2 of the norm.dist functions. If we're finding a greater than probability, we need to do 1 minus a norm.dist. And if we're doing a less than or less than or equal to, we just do 1 norm.dist function. If we're looking for only A, the probability that x equals A. For example, if I take x equals 4, then that would be, on my graph, the probability of x equals 4 is given by that 1 bar. But to use the normal distribution, I'm going to look at the probability that x is between 3.5 and 4.5. I'll make my graph a little bit easier so you can see what I'm actually drawing. So for the 3.5 to 4.5, x is between that. 3.5 and 4.5 are the edges of our bars. So in order to find the probability using the normal distribution, I'm going to follow the blue curve this time, and we'll find this probability. And you can see that it is very close. It's a little off, but that's also because we have a very small n at 10. The larger the value of n, the more accurate the normal approximation will be. So I'm using a small number so that we can visualize it and actually color things in. So exactly equal to 4, probability x is equal to a number. We're going to use the normal and do the probability that x is between the boundary values. So here in my graph, the orange represents the probability x equals a number, and this is binomial, and the blue is the probability that x is between two numbers, 3.5 and 4.5. Let's try another one. So let's look at the binomial probability x is greater than or equal to a. Greater than or equal to a means all values a and greater. So if we were changing this to an actual number, we would say the probability that x is greater than or equal to 4. Over here on my graph, greater than or equal to 4 means we're taking the bar that represents the probability for 4 and all the bars to the right because we are greater than. So what value do we need to choose for the normal distribution to make sure that we capture all of those bars to the right? We need this value just below 4, the boundary value 3.5. If I now draw my corresponding normal distribution in blue, and you can see how when we do this, we're also picking up some blank spaces, and that helps to correct for the extra up top. So again, blue, probability that x is greater than 3.5, and the orange, probability x is greater than or equal to 4. So if we were writing the normal distribution, probability x is greater than 3.5. Remember that this is a 1 minus a norm.dist function because we are greater than. Norm.dist only gives us less than values. Compare this problem to the very next one. What do you notice about the one we just looked at compared to this new one? This is a greater than or equal to, and the next one is just a strictly greater than. So if we're doing a strictly greater than, we're looking for all values greater than A, not including A. And since we're not including A, x is greater than 4, and over here in our graph, greater than 4 means we're going to skip the 4 and go right over into all the bars that are greater than 4, directly to the right. Contrast that with the normal distribution. We want to start the normal at the other boundary value for 4.5. So probability that x is greater than 4.5. This is another 1 minus norm.dist function. And so 4.5, following the normal distribution curve, will give us a good approximation of that binomial distribution. Let's look at less thans. Things go a little differently. It's difficult to come up with an always situation because it depends on the direction of the inequality. Draw the pictures out and check yourself, making sure that what you color in matches the problem in question. So here, probability that x is less than or equal to 4, all values less than and including A. Let's graph that one. 4 here. Less than or equal to 4. Equal to 4 gets us the 4 bar. Less than is left. And so our probabilities would be the bars for 4, 3, 2, 1, and 0. Finding the corresponding normal distribution, we see what's colored in. I want that value. That value is 4.5. So I'll take 4.5 and follow the normal curve down, and we'll take this area for the normal. Now, I'm not sure this has been mentioned before, so I will mention it here. When we have a discrete probability, we can find the probability of x equaling a value. Because it's discrete, there are a finite number of values that x can take. Each of those values of x has a probability associated with it. When we're looking at a continuous probability distribution, though, continuous probability distributions have an infinitely many number of values for our random variable x. When we're talking about the probability that x equals a very specific number in a continuous probability distribution, that probability is going to be 0. When you're looking at a pot of infinitely many marbles, it's impossible to figure out the probability of just one particular marble coming out. The concept of infinity is a pretty difficult concept, so if it's hard for you to grasp that, that's okay. Just know that when we're dealing with continuous probability distributions like the normal, the probability of equaling a particular value in the distribution is 0. So when we write our probabilities for the normal distribution, whether we use a less than or equal to sign doesn't matter. You can use either. In our class, they're interchangeable because the probability of something equaling a number, equaling a particular value, is 0. Just know that that symbol doesn't matter too much for our normal distribution. Okay, so how would we write that in general for our normal? We would write probability that x is less than 4.5. And then similarly, x is less than 4, not including 4. All values less than a, not including a. So if we're looking at the probability, x is less than 4. For example, I can come over to my graph and I've got 4 right here. Strictly less than 4 means we're going left of the 4 bar. So corresponding that to our normal distribution, we need the value directly left of 4, 3.5. And we'll take 3.5 all the way up to the normal distribution and color all of that area in. And I hope these graphs help you visualize what you need to find, how you use that continuity correction when you transition from a binomial probability question to using the normal for approximation. In all of these cases, the mean is n times p. The standard deviation is the square root of n times p times q. and we're satisfying that NP greater than 5 and Q greater than 5. The last two have to happen in order for the normal distribution to even be a good approximation of the binomial. So that's the first thing that we'll check when we're trying to use this method. Some things that I didn't show in this table are betweens. I didn't do probability that x is between two numbers, but I will do that in the examples.